Gravity is not a force. That sentence should sound wrong. Gravity pulls things down. It holds the planets in orbit. It keeps your feet on the ground. How could it not be a force? But I mean this literally. According to general relativity, the theory that has passed every experimental test for more than a century, gravity is not a force acting on objects. It's a feature of space-time geometry. Objects in freefall are not being pulled by anything. They're moving in straight lines through curved space-time. And the reason this feels like a force is because we're not in freefall. We're being pushed by the ground beneath our feet. I'm Leonard Susskind, and after 50 years of working with Einstein's equations, I've come to see gravity in a way that still feels counterintuitive even to me. Gravity is geometry, curvature, the shape of space-time itself. And once you understand that, everything about how the universe works, from falling apples to black holes to the expansion of the cosmos, becomes clearer. Let me show you why gravity is not what you think it is. Start with what Newton taught us. Gravity is a force of attraction between masses. Every object with mass exerts a gravitational pull on every other object. The strength of that pull depends on the masses and the distance between them. The Earth pulls on you, you pull on the Earth, the sun pulls on the planets pull back. It's mutual. It's universal, and it works. Newton's law of gravity is extraordinarily successful. It predicts planetary orbits, it explains tides, it guided the Apollo missions to the moon. For most practical purposes, it's correct. But it has a problem, a deep conceptual problem that bothered physicists for centuries. How does gravity work? How does the sun know the Earth is there across 150 million kilometers of empty space? How does the gravitational force travel? Is it instantaneous? If the sun suddenly vanished, would the Earth immediately fly off in a straight line, or would it take time for the loss of gravity to propagate? Newton himself was uncomfortable with this. He called it action at a distance and admitted he had no explanation for how it worked. He could calculate the effects perfectly, but the mechanism was a mystery. Einstein solved it. But the solution was so radical that it took decades for physicists to fully absorb it. In 1915, Einstein published General Relativity. And the core idea is this: gravity is not a force. There is no gravitational pull. What we experience as gravity is the curvature of space-time caused by the presence of mass and energy. Objects move through curved space-time along paths called geodesics, the straightest possible paths in a curved geometry. And those paths, viewed from the outside, look like they're being deflected by a force, but nothing is pulling. The space itself is curved. Let me make this concrete. Imagine you're in a spaceship far from any planet or star. You're floating, weightless. You release a ball, and it stays exactly where you put it. It doesn't fall. There's no gravity. Now imagine the spaceship starts accelerating. The floor rushes up to meet you. You hit the floor. The ball falls. If you didn't know the spaceship was accelerating, you'd swear you were in a gravitational field. Everything behaves exactly as if gravity were pulling you down. This is called the equivalence principle. And it's the key insight. Being in a gravitational field is indistinguishable from being in an accelerating reference frame. They're the same thing, not similar. The same. This means if you're standing on Earth's surface, feeling weight, you're not actually experiencing gravity. You're experiencing the force of the ground pushing up on you, preventing you from following your natural path through space-time. The natural path, the geodesic, is freefall. An apple falling from a tree is not being pulled down by gravity. It's moving along a geodesic, the straightest path through curved space-time. You, standing on the ground, are not on a geodesic. You're being pushed off it. The ground is exerting a force on you. That force is what you feel as weight. In other words, free fall is the natural state. Standing still is the forced state. This is backwards from how we normally think about it. We think standing on the ground is natural and falling is forced, but general relativity says the opposite. Falling is natural, standing is forced. Let me give you another way to see this. Imagine you're an astronaut on the International Space Station. You're orbiting Earth at 400 kilometers altitude, traveling at about 7.7 kilometers per second. Are you being pulled by Earth's gravity? Most people would say yes. The gravitational force is holding you in orbit. But that's not correct. You're in free fall. You and the station are both following geodesics through space-time curved by Earth's mass. You're not being pulled, you're following the natural path. The reason you orbit rather than flying off in a straight line is because space-time is curved. A straight line through curved space-time is a circle around the Earth. From your perspective, inside the station, there is no gravity. You float, objects float, nothing falls. You are in an inertial reference frame, a frame where Newton's first law holds exactly. Objects at rest stay at rest. Objects in motion stay in motion. No forces are acting. The ground, by contrast, is not an inertial frame. Standing on Earth's surface, you are being constantly accelerated upward by the electromagnetic force between your feet and the ground. That acceleration is what you feel as weight. Einstein realized this in what he later called the happiest thought of my life. He was sitting in his office in Bern in 1907, and he imagined a person falling off a roof. The person would feel weightless. They wouldn't feel gravity. Because in free fall, you're not experiencing gravity. You're moving naturally through space-time. This led Einstein to the conclusion that gravity is not a force in the usual sense. It's the curvature of space-time. And that curvature is determined by the distribution of mass and energy. The mathematical expression of this is Einstein's field equation. It's one of the most beautiful equations in physics. Gmu nu equals 8 pi Tm nu. On the left side is a tensor describing the curvature of space-time. On the right side is a tensor describing the distribution of mass and energy. The equation says mass and energy curve space-time, and that curvature tells objects how to move. John Wheeler summarized it perfectly. Space-time tells matter how to move. Matter tells space-time how to curve. Now, let me give you the experimental proof, because this is not just philosophy, it's been tested rigorously, repeatedly, and it always works. First, the bending of light. In 1919, Arthur Eddington led expeditions to observe a solar eclipse. During the eclipse, stars near the sun became visible, and their positions were shifted slightly but measurably from where they should have been. The light from those stars had passed near the sun on its way to Earth, and the sun's mass had curved space-time, bending the light's path. Newton's theory predicted a small deflection, but Einstein's theory predicted twice as much. The measurements matched Einstein. Light follows geodesics through curved space-time. Even though light has no mass, it's affected by gravity, not because gravity pulls on it, but because space-time is curved. Second, gravitational time dilation. Clocks run slower in stronger gravitational fields. This has been measured countless times. Atomic clocks on mountaintops tick faster than clocks at sea level. GPS satellites have to account for this. Their clocks run about 45 microseconds per day faster than Earth's surface. Without this correction, GPS would accumulate errors of several kilometers per day. The most elegant test was the Pound-Rebka experiment in 1959. Using gamma rays in a 22 5-meter tower at Harvard, they measured gravitational redshift with extraordinary precision. Photons traveling upward lost energy. Photons traveling downward gained energy, exactly as general relativity predicted. Light climbing out of a gravitational potential gets redshifted because space-time is curved and time flows differently at different heights. Why does time dilate? Because space-time is curved. Time is one dimension of space-time, and curvature affects it just as it affects space. Third, gravitational waves. In 2015, LIGO detected ripples in space-time caused by two black holes colliding 1.3 billion light-years away. These ripples, gravitational waves, are exactly what general relativity predicts. When massive objects accelerate, they create distortions in space-time that propagate outward at the speed of light. We've now detected dozens of gravitational wave events. Every one matches the predictions of general relativity perfectly. Gravitational waves are not waves of gravitational force. They're waves of space-time curvature. The geometry of space and time itself is oscillating. Here's another piece of evidence that's deeply strange. The Shapiro delay. Radio signals sent past the sun take longer to reach their destination than they would in flat space-time. Not because the sun's gravity slows the signal down, radio waves travel at the speed of light regardless, but because space-time near the sun is curved and the geodesic path the signal follows is longer than it would be in flat space, the signal travels the same speed but through a curved geometry, so it takes more time. This was first measured in the 1960s by bouncing radar signals off Venus when Venus was on the far side of the sun from Earth. The delay matched Einstein's prediction to within experimental error. All of this confirms the same picture. Gravity is not a force pulling on objects. It's the curvature of space-time, and objects move along geodesics through that curvature. Now, let me address the obvious objection. If gravity is not a force, why does it feel like a force? Because you're not in free fall. You're being pushed. When you stand on the ground, the electromagnetic forces between the atoms in your feet and the atoms in the ground prevent you from following your geodesic. The ground exerts an upward force on you. You feel that force as weight. That force is real. But it's not gravity. Gravity is the absence of force. The ground is the force. If the ground suddenly vanished, if you stepped off a cliff, you would stop feeling that force. You would feel weightless. Not because gravity disappeared, but because you're now in free fall, following your natural geodesic through curved space-time. This is why astronauts in orbit feel weightless. Not because there's no gravity. Earth's gravitational field at 400 kilometers is still about 90% as strong as it is on the surface. They feel weightless because they're in free fall. They and the station are both following geodesics. No forces act on them except for air resistance and tiny tidal effects. Let me make this even more concrete with a thought experiment. Imagine you're in an elevator with no windows. The elevator cable snaps. You start falling. What do you feel? Nothing. You float. Objects around you float. You're weightless. Even though you're falling toward the Earth at 9.8 meters per second squared, you don't feel it. You don't feel gravity because you're in free fall. You're following your natural path through space-time. Now imagine someone outside the elevator grabs the cable and stops your fall. Suddenly you slam into the floor. You feel weight. That's not gravity appearing. That's the floor exerting a force on you, preventing you from continuing along your geodesic. The force you feel is the electromagnetic force from the floor, not gravity. Gravity is what you feel when nothing is stopping you from moving naturally, and what you feel in that case is nothing. Here's something even stranger. Tidal forces. These are the only thing about gravity that's truly measurable in a small region of space. Imagine you're in free fall near a black hole, feet toward the singularity, head pointing away. Your feet are slightly closer to the black hole than your head. The geodesic your feet want to follow and the geodesic your head wants to follow are slightly different because there are different distances from the mass. This difference stretches you. It's called tidal force, and it's what would eventually tear you apart near a black hole. But notice, you don't feel your feet or your head being pulled. You feel yourself being stretched. The difference between geodesics creates stress in your body. That's measurable. That's real. And that's the only local manifestation of gravity. In general relativity, gravity is encoded in the curvature of space-time, and the only thing you can measure locally is tidal forces, the difference in geodesics across a finite region. There's no local measurement you can make that detects the gravitational field at a single point. There are only geodesics and differences between geodesics. Here's something even stranger: frame dragging. Rotating masses don't just curve space-time, they twist it. They drag space-time around with them as they spin. This was predicted by Einstein in 1918, but wasn't confirmed until 2011 with the Gravity Probe B satellite. The satellite carried 4 ultra-precise gyroscopes in orbit around Earth. Over a year, the gyroscope's orientation drifted by a tiny amount, about 39 milliarcseconds, exactly as general relativity predicted. Earth's rotation was dragging space-time around it, and that dragging pulled the gyroscope's axes along. Near a rotating black hole, this effect becomes extreme. Space-time is dragged so strongly that nothing, not even light, can remain stationary relative to a distant observer. Everything within a certain distance, called the ergosphere, is forced to rotate in the direction of the black hole's spin. You can still escape the ergosphere, unlike the event horizon, but while you're in it, you cannot stand still. Space-time itself is moving. This is not a force. This is geometry. The black hole's rotation has shaped space-time into a geometry where standing still is impossible. Your geodesic is dragged around the black hole whether you like it or not. Now let me connect this to something even deeper. The equivalence principle tells us that locally, in a small enough region of space, you can't tell the difference between being in a gravitational field and being in an accelerating frame. They're identical. But here's the thing. We know electromagnetic forces are real. We can shield against them. We can measure them with instruments. We can turn them on and off. Gravity, by contrast, you cannot shield. You cannot turn off. You cannot measure locally except through tidal effects. And everyone, regardless of their mass or composition, falls at the same rate in a gravitational field. This is called the universality of freefall, and it's been tested to extraordinary precision. A hammer and a feather fall at the same rate in vacuum as the Apollo 15 astronauts demonstrated on the moon. Gold and aluminum fall at the same rate. Dark matter and ordinary matter fall at the same rate. Everything falls at the same rate because they're all following geodesics, and geodesics don't depend on what's moving along them. This universality is built into general relativity. It's not an accident. It's a consequence of gravity being geometry rather than force. Let me end with the most mind-bending consequence of all this. If gravity is not a force, then what is the universe expanding into? The answer is nothing. The universe is not expanding into anything. Space itself is expanding. The distance between galaxies is increasing not because they're moving through space, but because the space between them is being created. Space-time is dynamic. It can curve, stretch, ripple, expand. And general relativity describes all of this as geometry, not as forces acting on things. The expansion of the universe is not something happening in space. It's something happening to space. And that's only comprehensible once you accept that space-time is a physical thing capable of changing its shape, and that gravity is a manifestation of that shape rather than a force acting through it. I know this is hard to absorb. Gravity as geometry feels wrong at an intuitive level. We evolved to think of gravity as a force pulling us down. Our entire experience tells us we're being pulled toward the Earth. But our experience is misleading. We're not being pulled. We're being pushed by the ground, by the chair, by whatever is preventing us from falling freely through curved space-time. Free fall is natural. Standing is unnatural. Gravity is not a force. It's the shape of the universe. And once you see it that way, everything changes.